Imagine, for a moment, standing at the very edge of everything, a place where mathematics ends and physical reality begins, where time doesn't flow forward or backward, it simply is. You know, for more than a century now, physics has been captivated by this beautiful, almost haunting dream: the search for one single equation, one elegant piece of mathematics that could describe the entire universe. A master key that could unlock both the world of the very large, gravity, space-time, the silent waltz of galaxies, and the world of the very small, that strange, chaotic realm of particles and quantum forces. Some people call it the theory of everything. Others have called it the God equation. Whatever name you give it, it's like the last great intellectual mountain for humanity to climb. And for 100 years, it's always been just out of reach. Even the great Albert Einstein, he spent the last 30 years of his life completely dedicated to this quest. After he finished his masterpiece, the theory of general relativity, he was convinced he could find what he called a unified field theory. He was sure he could build a bridge between the elegant cosmos he had described and the bizarre new world of quantum mechanics. But he never found it. He died leaving behind what is, without a doubt, the greatest unsolved problem in all of science. So let's really dig into why this is so hard. The problem is that our two best theories of the universe, well, they hate each other. They're fundamentally incompatible. On one side, you have Einstein's general relativity, and it is just a thing of sublime beauty. It describes gravity not as some mysterious force pulling things together, but as the actual curvature of space-time itself. Massive objects literally bend the fabric of reality around them, and other objects just follow those curves. This theory perfectly describes the orbits of planets, the way light bends around black holes, the expansion of the entire universe. It's a world that is smooth, continuous, and best of all, deterministic. If you know the starting conditions, you know exactly what's going to happen. But then there's quantum mechanics. And this theory describes the world of the incredibly small. It's a world of particles that can be in multiple places at once, a world where things can tunnel through solid walls, where particles can become entangled, linked in this mysterious way across vast cosmic distances. Einstein famously called it spooky action at a distance. And unlike relativity, this world is all about probability, not certainty. It's fuzzy, it's chaotic, and it's deeply, deeply weird. So for decades, the smartest people on the planet have been trying to stitch these two realities together. They've come up with some incredible ideas, like string theory, which says maybe every particle is just a tiny vibrating string in extra dimensions, or loop quantum gravity, which suggests that spacetime itself is pixelated, made of tiny, indivisible chunks. But every single time, they slam right into the same wall. A wall of mathematics so outrageously complex, so vast, that no human mind and no classical computer could ever hope to solve. So what do you do? What do you do when you face a problem so profound that it breaks all of your existing tools? Well, it started to become pretty clear to a lot of physicists that we didn't just need a faster computer. A bigger calculator wasn't going to cut it. We needed a completely new way of computing, a new kind of machine. One that doesn't think in the linear, step-by-step way that we do, but one that instead speaks the universe's native language, a language of probability and superposition, the language of quantum mechanics itself. So what's the secret sauce here? What makes these machines so different? Well, it all comes down to this one fundamental concept: the qubit. Now, you know how a normal computer works, right? Everything, your phone, your laptop, it all boils down to bits. And a bit is incredibly simple. It's either on or it's off, a 1 or a 0. That's it. A simple, definite state. But a qubit is a whole different beast. Thanks to a bizarre quantum property called superposition, a qubit can be a 0 and a 1 at the exact same time. It exists in this weird, shimmering cloud of probability, a blend of all possible answers. Think of it this way. A classical bit is like a light switch. It's either on or it's off. A qubit is more like a dimmer dial. It can be fully on, fully off, and every single possible value in between, all at the same time. And that ability, the ability to hold multiple values at once, is the fundamental source of a quantum computer's power. This maze analogy is probably the best way to really get your head around the difference this makes. So imagine you're faced with a giant, unbelievably complicated maze. A classical computer, the one in your phone, tackles this maze the same way you or I would. It picks a path, it goes down a corridor, hits a wall, oops, dead end, so it has to backtrack, go all the way back to the last junction, and then try another path, and then another, and another, one by one by one. It's methodical, it's sequential, and for a truly massive maze, it would take an eternity. Now look at the quantum approach. A quantum computer, because its qubits are in superposition, doesn't pick just one path. It explores every single path in the entire maze simultaneously. Imagine that for a second. Every possible left turn, every right turn, every corridor, every dead end, all of them are explored in the exact same instant. It's what's known as massive parallelism. The solution to the maze then emerges from this incredible process of interference, where all the wrong paths basically cancel each other out, and the correct path gets amplified. It's a fundamentally different and profoundly more powerful way of solving problems. Okay, so this quantum dream, this idea of a new kind of computer, has been around for decades. But then, December 2024 happened, and everything changed. Deep inside a lab in Santa Barbara, California, Google's quantum AI division pulled back the curtain on a new processor. Its name was Willow. And with its arrival, the game fundamentally changed. Now, I've been making this sound pretty amazing, right? But for years, quantum computing had this one giant, show-stopping Achilles heel. It's a problem called decoherence. You see, these quantum states, these delicate superpositions, are unbelievably fragile. I mean, ridiculously, impossibly delicate. The slightest vibration from a passing truck, a tiny fluctuation in temperature, a single stray microwave photon from the outside world can cause the whole beautiful quantum state to just collapse. Poof. It decoheres. The quantum information leaks out into the environment, and your calculation is ruined. And here's what was so frustrating for researchers. For years, when they tried to build bigger, more powerful machines by adding more qubits, they often just made the problem worse. More qubits meant more points of failure, more ways for noise and errors to creep in and destroy the calculation. It was like trying to build a giant, intricate sandcastle while the tide is coming in. It kept the entire field trapped in the realm of cool science experiments, but not much more. But then came Willow. The team at Google had finally cracked the code. They achieved what had been the holy grail of the field for decades, something called below-threshold error correction. Now, this is the magic part. For the very first time in history, when they added more physical qubits to the system, the overall error rate of the calculation actually went down. Let that sink in for a moment. The machine got better as it got bigger. Willow was sophisticated enough to use some of its qubits as watchdogs, constantly checking the other qubits for errors, and then correcting those mistakes on the fly, in real time. It could hold on to that fragile quantum state. It could maintain coherence long enough to do something truly meaningful. This was the turning point. This was the moment that the quantum computer stopped being a delicate laboratory curiosity and finally became a true, powerful scientific instrument, a tool that you could actually rely on. So you've just built the most powerful computational instrument in human history. What's the first thing you do? You give it a test. A really, really hard test. The team designed a specific calculation to prove what the field calls quantum advantage. Basically, to perform a task so mind-bogglingly complex that it would be practically impossible for any classical computer on Earth, or any we could ever imagine building, to ever solve it. The task they chose was to simulate the behavior of a complex quantum system. And they calculated that for the world's most powerful supercomputer, a machine that fills a warehouse and consumes megawatts of power, it would take, well, that number you see on the screen. That's 10 septillion years. That's a 1 with 25 zeros after it. Let's just try for a second to wrap our heads around how big that number is. The entire universe, from the Big Bang until this very moment, is about 13.8 billion years old. This calculation wouldn't just take longer than that, it would take trillions upon trillions of times longer than the entire age of existence. It's a number that, for all human purposes, is infinite. It's a number that simply means never. And Willow completed the calculation in under 5 minutes. Seriously, let's just pause on that. A task that is effectively infinite for our entire technological civilization was finished in the time it takes to make a cup of coffee. This isn't just an incremental improvement. This isn't your new phone being a little bit faster than the old one. This represents a leap into a completely new computational reality, a fundamental shift in what is possible. Okay, so the result itself was just astounding. The what was mind-blowing. But it was the how that started to raise some deeper and, frankly, much more unsettling questions. The sheer density and speed of that calculation, it seemed to be pushing against the very limits of what our physical reality should be able to contain. So you have to ask, where could such an enormous computation possibly be taking place? Think about it this way. Computation isn't abstract, it's a physical process. It requires energy. It requires physical states to store information. It takes up space. So if the number of parallel calculations being explored by Willow at the same instant is vastly greater than the number of atoms in the processor itself, you run into a very, very strange problem, a physical paradox. Where is all that work actually being done?
Where's the scratch pad for this impossibly large calculation? Where's the information being stored?
And this very question is what led Dr. Hartmut Neven, the head of the entire Google Quantum AI lab, to drop an absolute bombshell in the official press release. He said, and I'm quoting him directly, "The results lend credence to the idea that quantum computation occurs in many parallel universes." I mean, just let that hang in the air for a moment. This wasn't a philosopher or a science fiction author. This was the lead scientist on the project, suggesting that his machine might be providing the first computational evidence for one of the most mind-bending ideas in all of physics.
Now, before you dismiss this as pure science fiction, you have to understand this is not some crazy new idea they just cooked up. The many worlds interpretation is a serious, legitimate scientific theory that's been around since way back in 1957, first proposed by a physicist named Hugh Everett. The core idea is this: every time a quantum system is faced with a choice, every time a particle could be here or there, every time an atom could decay or not, the universe doesn't pick one outcome. Instead, it splits. A new branch of reality is created for each and every possible outcome. So in one universe, the particle is here. In another, identical universe, it's there. For decades, this was seen as untestable, more of a philosophical curiosity than hard science. But there have been physicists like the brilliant David Deutsch at Oxford University who've been arguing for years that quantum computers are the proof. They say the only logical way to explain where all that immense computing power comes from is that the computer is harnessing resources from these other parallel realities. And Willow's calculation? Well, it's the first major piece of experimental data that seems to point in that extraordinary direction.
Okay, so let's take a deep breath. Does this mean we've officially proven the multiverse is real and we've solved the theory of everything? No, absolutely not. And we need to be very, very clear about this. Willow hasn't given us the final answer on a silver platter. What it has given us is a new key. A key that has unlocked a door to a room filled with mathematics and physics that humanity could never, ever enter before. It allows us to finally start asking entirely new kinds of questions, and, for the first time, it gives us a way to actually test the mathematics of theories that, until now, were completely beyond any hope of computation. And if this tool can really be used to probe the fundamental laws of physics, the potential applications are just staggering. I mean, look at this list. In energy, we might be able to understand and maybe even harvest power from the quantum foam, this roiling sea of virtual particles that pops in and out of existence in even the most empty space. In medicine, we could simulate molecular interactions with perfect accuracy, designing life-saving drugs atom by atom in a matter of days instead of decades. We could custom design new materials that don't even exist in nature, like room temperature superconductors that would completely revolutionize our energy grid and our world. And in cosmology, for the big questions, we could finally begin to simulate what's really happening inside a black hole, or watch the first few microseconds after the Big Bang unfold on a screen. These aren't just small steps, these are whole new frontiers of science. But, and this is a really important but, it's absolutely essential that we maintain a healthy dose of scientific caution here. A powerful new tool is not the same thing as an answer. The specific calculation that Willow performed, as incredible as it was what physicists call a toy problem. It was a very specific, carefully constructed task designed to do one thing and one thing only: prove quantum advantage, to show that the machine worked as intended and could beat a classical computer. It was not, in and of itself, a discovery of a new law of physics. The physicist Dr. Sabine Hossenfelder put it perfectly when she said, "A quantum computer performing a useless calculation very quickly is not the same as solving fundamental physics." And she is absolutely right. This achievement is the starting line of a new marathon, not the finish line. In the end, this brings us back to a much more cosmic, a more humble perspective. The great physicist John Wheeler, who actually coined the term black hole, once said, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance." Google's Willow processor hasn't eliminated that sea. What it has done is dramatically expand our little island of knowledge. And in doing so, it has revealed an even vaster, more mysterious shoreline of things we don't yet understand. We have built a machine that, for the first time, is beginning to speak the universe's language more fluently than we ever could before. Now, the great challenge and the great adventure is to listen very carefully to what it has to say.